Hello everyone, welcome to the lecture series on Foundations of Deep Learning, Concepts and Applications. We have started with the explainable AI, and in the last session we have seen what is the need for an XAI, and then we have looked into the two methods. One is PCI, second is occlusion. We will look into, in this particular session, we will explore SHAP, which is Shapley additive explanations, and the second method LIME, which is local interpretable model agnostic explanations. Let us get started with the SHAP. Now, when you look into this particular image, the whole concept here is once the model gives the prediction, we need to understand which are the pixels or which are the features which has contributed a lot for model prediction. That is the whole concept of explainable AI. So, in this today we are looking into the SHAP. Now, since we are dealing with an image, we know that for an image the features are usually an individual pixels, or it can be a group of pixels. When we say group of pixels, we call it as superpixels or we call it as segments. Therefore, what exactly is a superpixel? Superpixel is a small region of an image where all the pixels look similar. Now, if you look into this particular, this is one superpixel where all the pixels within this particular region look similar. Instead of treating every pixel separately, we group them, we group pixels into a larger chunks. Why is that we have to do? Because we are dealing with images. Ultimately, the algorithm that we will be using or the model that we will be building is a CNN. Now, for a CNN, single pixel does not contribute anything. So, single pixel is just one dot here, one dot here, one dot here. So, a single pixel really does not contribute anything for a CNN, or rather CNN does not understand what is the information which is present in that one particular pixel, but CNN understand the patterns. Therefore, superpixel captures edges, shapes, texture, which matters more than a single pixel. So, what is the aim here? So, the aim of a SHAP here is to understand which are the features which contributes to a model prediction. So, rather than taking an individual pixel, here we are grouping pixels together into a smaller region. We call that as a superpixel. So, superpixel is a small region of an image where all the pixels within that region look similar. So, with this, what exactly is the aim of SHAP? So, SHAP here explains which region of an image influence to model prediction. So, how do we do this? Whatever is the input image is now divided into many superpixels. There is no restriction that the superpixels should be 3, 4. We are dividing it into many superpixels. Once we do this, we are going to create a perturbed versions. What do you mean by perturbed versions? Some superpixels are on and some superpixels are off. How do it looks? It looks something like this. Here are the perturbed instances. We can see that there are some superpixels which are on and there are some superpixels which are off. All these are the superpixels which are off. All these are the superpixels which are on. So, by doing this, we are going to get an perturbed instance of an original image. Here you see this is a second perturbed instance where there are many superpixels which are off. Here, this is a third perturbed instance where there are a few superpixels which are off. So, how do the SHAP explains which regions are important? The first step here is we are going to divide an image into superpixel and then we are going to create an perturbed instance. How do we create a perturbed instance? Some superpixels we keep it and some superpixels we mask it. So, by doing this we are creating a perturbed instance. Once we do, we are going to build a CNN model. and whatever the CNN model we are building, to this CNN model we are passing the original image, original data set, and we are going to get the prediction. So, what is the prediction here? What is the probability that the given image is a tree frog? So, the given for this particular image, the probability is 0.94, and a similar way we are going to capture this, and then we will be using this later, and then we all the perturbed instances which we have created, all of these images are also passed into the CNN model that is being built, and then we are going to get its probability. So, this perturbed instance, when we are passing to a CNN model, it is giving us the probability that this is a tree frog is 0.52. When this perturbed instance is passed to CNN model, it is giving us very less probability here, because if you look into this particular image, the important parts are being masked. Therefore, the model is totally confused. The model is not very clear what exactly is this particular. Therefore, the probability with which it is predicting that it is a tree frog is very, very small, very, very less. Now, when you look into this particular, when this image is passed into CNN model, the model is very confident, and it is giving us the probability that it is a tree frog is 0.91. Why? The model is very sure it is a frog. Why? Because important pieces are kept here. So, with this I hope you have understood how we are going to do. We are going to divide an image, and then we are creating an perturbed instances, and for original image and for all the perturbed instances we are going to pass it to CNN model and get the predictions. Then the most important here, we are going to calculate the Shapley values. So, how is that we are going to calculate? This is the formula using which we are going to calculate. In this, what exactly this is going to explain? How much one feature contributes to model's prediction. Here ultimately we want to understand which are the features which have contributed for model prediction, right. So, how is that we are going to do? SHAP is going to calculate something called as an Shapley values. These values are something which will tell how much each feature is contributing to model prediction. Now, when we talk about the feature, if at all if you are dealing with the tabulated data, where you have data in the form of a CSV file, then here the features are probably the age, the blood pressure, the cholesterol, income, etc. You know, the columns here actually are the features. So, the SHAP tells how much each column contributes to the prediction. But here we are dealing with an image. So, for an image, what exactly is a feature? Feature is not a pixel here, feature is a superpixel. Why it is a superpixel? Because just one pixel does not contribute anything for model. CNN does not understand just with one pixel. Therefore, we are dealing with collection of pixels, and that collection of pixel we call it as superpixels. And SHAP will treat each superpixel as one feature, and SHAP computes how much that superpixel contribute to model prediction. So, here this is all about the feature, but let us get back to this formula and then understand what each of these terms meaning. First, let us try to understand what exactly is this. This is a SHAP value for a feature I. So, for a feature I, for a feature, this particular feature I, what exactly is the SHAP value, and what this value tells us how much did the feature I contribute to final prediction. So, this particular value will tell how much the feature I contributes to the final prediction. Then we have something called as F and we have S. What is F and S? F is a set of all features. When we say features, a feature here are superpixels, because we are dealing with the images. So, how many such features we have captured or we are considering, that is F. And what is S? S is a subset of features that does not include I. So, understand this theory statement. S is a subset of features that does not include I. What is the meaning of this? Suppose if we have considered F as totally 3 superpixels, 3 features, the entire image is divided into 3 superpixels. Let those 3 we call it as A, B, C, and I is C. If this is the case, go back to this particular definition. What does it say? It is a subset of features that does not include I. So, now create all the subsets which does not include C. So, if a set is having the elements A, B, C, then write all those subsets which does not include C. So, these are the possible subsets where there is no C present, correct? This is actually a subset S. So, there are 2 terms we have defined, one is F, second is S. F is a set of all features, and the features here is a superpixel, and S is a subset of features that does not include I. For example, if you take F as A, B, C and then I is C, then all those set where there should not be a term C. So, this is actually a set subset S. So, I hope these 2 terms are clear to us. Then let us look into the next 2 important terms in this particular formula. First, let us understand what exactly is this term. This will tell us how much does the output change when we add a feature I to S. So, this is one important term. It is going to explain us how does the output change when we add a feature I to the S. So, we will understand this with an example, and the next important concept here is this particular fraction. Because there is a divided term, we are going to get in terms of a decimal, and what is this fraction tell? This fraction tell us how much importance to give to a particular subset S. How important this subset is, this is the term which gives us the value. In short, this term is nothing but the weight. So, this is all about the Shapley values. We will understand this with an example. Now, this is the original image that we have. This is the original image. Now, this original image will be divided it into many superpixels. For understanding, let us assume we are dividing it into 3 superpixels. Now, what are those? The image is divided into 3 regions. Let us assume the image is divided into this, the image is divided into, and the image is divided like this. The image is divided it into 3 superpixels. In reality, it will not be dividing it into 3 superpixels, it will divide into many 50s, hundreds of superpixels. For understanding purpose, let us assume it is dividing it as 3 superpixels. This is a superpixel A, this region is a superpixel C and a B, and this is superpixel C. Okay, I hope this is clear to you. Once we do, now what is F? F is a number of such features we have considered. Now, for a SHAP, the feature here is a superpixel. Therefore, F is equal to ABC. And what is the cardinality of F? The cardinality of F is 3. What is this 3? 3 divisions, totally 3 segments that we have done, 3 features that we have considered. Those features here are superpixels. Now, once we complete this, the very first step is, because F is equal to 3, totally create a subset of 2 to the power of 3. In general, it is 2 to the power of n. Since n here is 3 such features we have considered, therefore, create a subset of, and the size is 2 to the power of 3. So, totally 8 different subsets we have to create. Now, when we consider f is equal to a, b, c, the possible subsets are, we will have an null set, null where there are no, and then we will have a, b, c, we will have a b, AC, BC, and the last set is ABC. So, these are the possible subsets. So, once we do this, how do we understand what exactly is the meaning of each of this? When we say it is a null set, which means you have not considered any of the superpixel. When you consider a mask, sometime back you have seen that when you go to an perturbed instance, here no superpixels have been considered. Almost every region will be all patches only. That is the meaning of there are no values. So, this is what is there are no elements, no superpixels that are being considered. And what does the meaning of A? Only A is considered, which means our set, our image looks something like this, where only rest everything is being masked, only a superpixel A is kept. Then only B, something it looks this way. So, this is where only rest everything is being masked, only this part of the superpixel is kept. Then it is a C. How does the C looks? If this is a C, rest all of the region is being masked, and only C is being kept, and this is how the image looks. And what exactly is AB? AB is where we are placing both A and B. This is A. This is a B, rest all portion of the image is masked. Similar way, you can imagine how AC looks, how BC looks. Finally, ABC, it is something in this way. So, all the regions have been kept, all the superpixels have been considered. Once you create a subset, the next step is pass, we have built a CNN model, pass this image to a CNN model, and then get the prediction, what is the probability that this is a dog, frog, this is a tree frog. Then pass this particular image and get the prediction, what is the probability that this is a frog, what is the probability that this is a frog. So, for every of the perturbed instances, pass it to CNN model and get the model prediction. So, the meaning of this is, when none of the superpixels are considered, the probability that it is predicting that as frog is just 0.1. This is just a random values that are being placed for an understanding purpose. When only this superpixel A is kept, and when we pass this image into CNN, the model is predicting that the probability that it is frog is 0.7. The probability that it is frog is 0.5 when only superpixel B is kept. What is the probability that, see, when we keep only this portion, so we doesn't even know what is the remaining part here. So, the model is not at all confident that it is a tree frog. So, we will see that there is a very less value. Similar way, when you pass each of these perturbed instance to CNN model, we are going to get the model prediction. First step, you have divided the image into superpixel, and then we have created a subset, all the possible subsets we have created, and then we have passed each of the subset, each of the image to perturbed instance to a model, and then we have obtained the model prediction. Now, this is important step. The next is, we are going to calculate the weights. So, what is that we are now calculating? We are calculating this portion of the, ultimately we should calculate this, right. In order to calculate, we are first calculating this portion. This is what we are calculating. Now, if you look into what exactly is the meaning of cardinality of S0, cardinality of S with 1, cardinality of S with 2, what exactly mean by this? In general, this cardinality of S gives us number of superpixels in that subset. That is the meaning of it, number of superpixels in that particular subset. When you say subset cardinality with 0, the meaning of this is a subset S has 0 superpixels in it. The subset has no superpixels. What is the meaning of this? Can you see here? Here there are no superpixels which are kept. Then what is the weightage that we should give to this subset? So, how is that we are calculating? Substitute the values back into this formula. So, this is now we are considering with for S0. So, which means this term is 0 factorial. Then F we know that it is 3. So, substitute it is 3 minus it is 0 minus 1. So, whole factorial. So, 3 minus 0 is 3 and 3 minus 1 is 2. So, we are seeing it is 2 factorial. First term is 0 factorial, 2 factorial, whole divided by cardinality of F. What is cardinality of F? It is 3. So, divided by 3 factorial. So, I hope you have understood how exactly to calculate this. So, and then substitute the values. 0 factorial is 1 and 2 factorial is 2 here, 2 into 1 is 2 and 3 factorial is 3 into 2 into 1 which is 6. So, calculate, you are going to get 1 by 3. So, similar way, now we calculate for cardinality S is equal to 1. What is the meaning of S is equal to 1? It is a subset. S is, we know that it is a subset. Subset S contains only one superpixel. Which are those subsets which contain only one superpixel? All of these, there is only one element, there is only one element, there is only one element. So, how much weightage should be given to this? How important is this subset? So, how is that you will calculate? Once again go back and then substitute the values. Since S is 1, this is 1 factorial, this is 3 minus 1 minus 1. So, it is 3 minus 2 which is 1 factorial and the first term is 1. So, we have 1 and divided by 3 factorial. So, we got 1 by 6. Similar way, we are now calculating for S is equal to 2. Now, what is the meaning of S is equal to 2? A subset containing 2 superpixels. Which are such subsets? Can you see there are 2 superpixels here? What are 2 superpixels? AB. There are 2 superpixels AC. There are 2 superpixels BC. So, S is equal to 2 indicates a subset containing 2 superpixels. Then go back and then substitute the values, we get 1 by 3. Now, you can ask the question, why we are not considering for, why are we not calculating this? Why we are not doing for cardinality of S with 3 or subset S containing 3 superpixels. Containing 3 superpixels is actually ABC. Why are we not doing? Go back to the definition of subset S. What exactly is S? S is a subset of features that does not include I. Now, here the set that we are considering is ABC. Now, all the superpixels are here. Now, you cannot write a subset which does not include all the elements you have considered. That is the reason why we will not consider calculate for S is equal to 3. I hope this concept is clear. So, what exactly we have done here? We have calculated the weight that has to be assigned. With this, let us proceed next. Now, we are calculating this part. Along with this part, we are also calculating this entire. Okay. So, I think I missed saying one more point. So, what is that? Now, how is that you will be understanding this 1 by 3, 1 by 6, again 1 by 3. What is the meaning of this? When calculating the Shapley values, subset with 0, this is subset with 0 superpixels contributes with the weight of 1 by 3. When we are calculating the Shapley values, subset with 1 superpixel contributes the weight of 1 by 6. Similar way, the subset with 2 superpixels contributes to a weight of 1 by 3. This is how we will read or understand each of these values. Now, let us understand the most important concept here, that is calculating the SHAP values. Now, we need to calculate this. In order to calculate, now we have calculated this part from the previous step. Now, we have to focus on this. Now, what exactly we are considering? We are considering a superpixel A. So, which means the features are A, B, C and I value is A. When I value is A, what all possible subsets we are considering? It is which does not include A. Which does not include A are all of these values. It is empty, B, C and B, C. So, it is all of these are the values that we are calculating. Now, let us try to understand this part first, and then I will put each of these values together. Now, in order to calculate the Shapley values, we are first computing this portion. Okay. Now, what exactly we are doing? To compute the importance of superpixel A. This is what we are calculating here. So, in order to calculate, to compute the importance of this superpixel A, we look for all possible subset S that does not include or that does not contain A, and measure this particular term. Now, this will tell us how much A increases the prediction when we add it to the different subsets. So, that is what we are going to do it. Now, let us see how we are going to calculate it. So, now what exactly is I here? I, what we have considered is A. Now, what is S we have considered? S is null. So, how is that you are going to calculate this value? It is f of S union, this is A minus f of S. So, if you take this, it is S is null, union which is A minus f of S is f of empty. So, now you know union is the complete. So, it is A minus f of F phi, which is null. So, what is f of A? What is the model prediction? So, when only A is kept, the model predicted value is 0.7. When no elements are considered, the model prediction is 0.1. So, go back and then substitute 0.7 minus 0.1, we are getting 0.6. So, this whole term what we got is 0.6. So, I hope this is clear to you how we are calculating. So, for understanding, I am showing you once again. Here we are trying to understand when A is being added, how it is going to, how much A increases the prediction. So, this is what we are calculating. What is the importance of A? When I add a superpixel A, how much it is going to increase the model's prediction? This is what we are trying to understand. Now, already we have calculated the weight. Now, we have to calculate this term. So, now what is S? S here is empty. So, substitute it is empty union. What is I we have considered? I we have considered it as A. So, superpixel A, right. So, this is A. Now, minus f of what is S? S what we have considered is empty. So, now it is union. So, when it is union, it is complete. So, it is A. minus f of phi. Now, what is this? This is a model prediction. So, what is f of a? When only a is kept, what is the model's prediction? 0.7. When none of the elements are kept, the model prediction is this. Just substitute the values, we got 0.6. Now, this is what is this particular term, but we still have, we have to multiply it with this term, right? What is this? When S is equal to 0, what is the weight? We have already computed when cardinality of S, when it is 0, the weight is 1 by 3. So, therefore, you are multiplying 1 by 3 with the 0.6. So, 1 by 3 multiplied it with 0.6, we are getting 0.2. Now, what exactly are these two values? What is this 0.6 and what is this 0.2? How to read? When only superpixel A is kept, the probability of predicting the frog increases by this value weighted to this value. This is how you need to read this. Understand, when a superpixel A is added or when superpixel A is kept, the probability of predicting it as a frog increases by this value plus 0.6 and weighted to 0.2. Similar way, you will calculate for each of this. So, let us do it for one more and then we will skip the remaining steps. So, let us now calculate what exactly is this. What is 1 by 6? S is equal to 1. There is only one element which is kept. When S is equal to 1, the value is 1 by 6. That is what is 1 by 6 here. How are we getting this? Let us go back and then substitute S of what is I value. I value what we have considered here is A. So, that is I value minus f of S as it is. Now, what is S? S is B. So, we are considering B union A minus f of B here. So, this is B comma A minus f of B. So, can we write this as AB minus f of B? So, what is the model's prediction when we have considered AB? So, when we have considered AB, what is the model's prediction? 0.75, 0.75 minus what is only when B is considered? 0.5. 0.5. So, calculate this and subtract and then divide it with, multiply it with 1 by 6, we are going to get 0.25 contributing with the weight 0.041. How to read this? Already we have B. There is an image where the superpixel B is there. For that you have added superpixel A also. With adding, by adding A to the particular image where only B is kept, then the probability increases by 0.25 weighted to this value. So, this is how you are going to calculate each of these. Similar way you will calculate for S is equal to C and then you will calculate for S is equal to BC. So, once you calculate each of these, finally we are going to add up all of these values. We are going to add up this. So, by adding we are getting this, we are rounding it off to this value. So, what exactly we have calculated here? Superpixel A contributes about plus 0.46 to model's final prediction. What we have calculated is the SHAP value. SHAP value for what? SHAP value for A. And what is the value that we are we have calculated? It is 0.46. And how to interpret this? The superpixel A, which is frog's face, contributes about plus 0.46 to model's final prediction. Similar way, now you will calculate for superpixel B. So, what are different features? Features are A, B, C, and what is I here? I now is B. So, what all subsets you have to consider now where there is does not include B. So, these are the possible subsets which does not include B. So, whatever you have computed before, the same steps have been repeated. Now, you will be calculating what is the importance when B is being added, how much we are going to see the difference in the prediction. So, we are calculating for B, and then the same steps have been repeated like superpixel A, and then we are getting the Shapley value for B. Similar way, we will be calculating for superpixel C, and without including C, does not include C, these are the subsets. So, for all of these you are calculating, finally we will calculate the Shapley values, Shapley value for C. So, I hope this is clear to you. So, for what we have done is we are calculating the Shapley value for A, B and C. How much each feature contributes to model prediction is what we have calculated. So, now whatever the values that we have calculated, this is the one. For A it is 0.46, B 0.28 and C it is 0.06. It is these values that we have calculated. Now, what are we understanding from this is, when the interpretation from these values is superpixel A contributes the most to model's prediction, then followed by B, then followed by C. It is an explainable AI, right? What is explainable AI? Ultimately, we should understand which are the features which have contributed to model prediction. Now, what we have calculated, what is the final interpretation? The superpixel A contributes a lot to model prediction, then superpixel B, then superpixel C. This is what we have calculated. And the last step, we have to calculate something called as, and we have to check the consistency. Now, how is that you will calculate the consistency? It is a difference between, if you look into, it is the difference between model prediction when all the features are present. This is when all the features are present. When all features are present, what is the model prediction? It is 0.9. When none of the features are present, what is the model prediction? The model prediction is thus. Now, what is consistency we are checking? It is a difference between the model's prediction when all the features are present and model prediction when no features are present. So, when you subtract, you are getting 0.80. Right. So, now what exactly is this 0.80? How is that you have to understand this? This is the total model prediction, and the total model prediction must be distributed fairly among the features. Which are the features here? The features are A, B and C. Now, the 0.80 has to be distributed fairly. Now, how is that it has distributed fairly? It has given 0.46 weightage for superpixel A, 0.28 for superpixel B, 0.06 for superpixel C. So, when you add up all of these, you will again get this 0.80. Why is that we have to do this? So, SHAP must always satisfy an important property called cooperative game theory. So, it has to satisfy this particular property. Because of this, we are checking the consistency, and then if you look into the consistency 0.80, when you take the difference between this and when you add up all of this, the value is coming up to 0.80, which means whatever the predictions that are the calculations made are correct. The importance that are computed by the SHAP values are correct. So, it has to be distributed fairly is the total effect that must be explained by the SHAP, that is what is the 0.80. And the last step for the visualization is whenever you execute explainable AI, we are going to get the output which will tell which are the pixel values which have contributed most, and it is important. Now, from the previous we have calculated the Shapley value for A is plus 0.46, which means because it is a plus, these are positively contributing. Not necessarily that every time we get positive values, sometimes for some calculations we may even get a negative also here, which means those superpixels are positively contributing. Where there is a negative, those superpixels are negatively contributing for model prediction. So, that is how we need to interpret here. Since it is 0.46, which is a higher value, those superpixels will have a strong red. You will see something like this. Then it is superpixel B, which is moderately important. You will see little less red, that is medium red. And superpixel C, which is very light, these are very less important features, but since it is positively contributing, you will see very light red or almost white. So, final interpretation will look something like this. This is one example of SHAP. You can see there are some which are more pink or more red. There are some which are blue here, which are negatively contributing. Blue here are towards negative, and red or pink is more towards the positive, and 0 is neutral. So, this is how the SHAP calculates the which features are contributing to model prediction. So, with this, let us now look into the next topic called LIME, and here LIME also performs more or less similar steps initially. So, what are those initial steps? First, take an image. The image is divided into many superpixels. Here the superpixels, as you can see here, one difference here is each superpixel in LIME is treated as a binary feature. Now, what is a binary feature here? In SHAP, what we were doing, some superpixels are kept and some superpixels are masked. So, here also we are going to do that. Those superpixels which we are keeping, we are going to give the value as 1, and those superpixels which we are masking, we will be giving the value 0. So, which means if an image is divided it into, for example, if it is divided into 50 superpixels, then we will have a vector of length 50 binary values. Those superpixels which are kept will get the value 1. Those superpixels which are not, we are not using those, we are not keeping that, then we will get the value 0. You can see here, this is one example where you have kept this superpixel, so you will get the value. You kept the superpixel value, you kept this, you have not kept, all of these will get 0. So, ultimately those superpixels which are kept, so if you see here, this is on, this is off, this is on, therefore, you will be representing it as 101. Why? Suppose if the image is divided it into 3, and then the vector will be of length 3. If an image is divided it into 50 superpixels, then the vector will be of length 50. Then how we were passing the perturbed instances to a model and get the prediction. Here also all these perturbed instances are passed to CNN model, and we are going to get the predictions. Here this particular image, when it is passed to CNN, it is giving us this probability. When this is passed to CNN model, it is giving us this probability. When this image is passed to CNN, it is giving us the probability of 0.91. So, what is the second method we are discussing here, which is LIME, and in LIME those superpixels which are kept will get the value 1, and those superpixels which are masked will get the value 0. So, here it is comma 1. So, it is 0, 0, 1. So, next, let us understand this with an example here, the working mechanism of LIME. So, here also the image is divided into 3 superpixels, superpixel A, superpixel B and superpixel C. And there is one important concept which you have to consider. When all the superpixels are kept, the value will be 1, 1, 1, because if the image is divided into 3, if all superpixels are kept, then the value is 1, 1, 1. This is important, remember this, we will get back to this point again. Then consider every possible subsets. So, if number of features here are 3, then the superpixel, then the subset will be 2 to the power of 3. These are different 8 combinations. Now, how we are going to understand what are these 0, 0, 0? The meaning of none is no superpixels are kept. So, when no superpixels are kept, all the values will be 0. Now, what is the meaning of A? Only A is kept, then B and C will be 0. B, only B is kept, A and C will be 0. C, only C is kept, A, B are 0. Similar way, AB are kept, C is 0. A and C is kept, are kept and B is 0. A is 0, B and C are kept, and finally all the features are considered. So, A, B, C, all the values are 1, 1, 1. So, which are the features which are kept and which are the features which are masked, accordingly place zeros and ones. Now, pass this image to a model and get this prediction. Pass the image where only A is kept and get the prediction. Similar way, pass each of these images and get the model prediction. That is what is f of s, where f of s is a model prediction. Next, we are calculating the difference. Look at this, how we are calculating the difference. We are calculating the difference by comparing it with original. What is original? Original is 1, 1, 1. And what we are considering here, we are considering for 0, 0, 0. When you take the difference, it is 1 minus 0 is 1, 1 minus 0, 1 minus 0, this. Next, you are keeping 1, 0, 0. Compare it with the original. 1 minus 1 is 0, 1 minus 0 is 1, 1 minus 0 is 1. Take the difference between this, compare it with the original and then write the differences. So, I hope you have understood how the difference is been calculated. Next is Hamming. Hamming is how many number of ones. Here number of ones here are 3. This is one way of calculating the distance. Number of ones here are 2. Number of ones here is 1, 1, 2, 2. So, you are writing the Hamming. Next, calculate the Euclidean distance. How is that you calculate the Euclidean distance? Take this under root, it is 1 square plus 1 square plus 1 square is equal, you are going to get this. Similar way, under root it is 0 square plus 1 square plus 1 square. Like this you calculate the Euclidean distance. So, from this from this particular table, what are we understanding? This leftmost is the number of the possible subsets 2 to the power of 3, and then which are the features which are kept, which are the features which are masked, which are kept 1, masked 0 accordingly. Then pass each of the image to a CNN model and get the predictions. Then calculate the difference. How are we calculating the difference? We are calculating the difference by considering with the original. What is original? Where all the features are kept. So, compare this with the original and calculate the difference. Then calculate the distance, and the distance is calculated using Euclidean formula here. Now, once you do this, the next step is we need to calculate the weight. Now, whatever the distance that we have calculated, from that you have to calculate the weight. And what is here, what is the formula for the weight here? It is exponential minus d, whatever is the distance divided by kernel width. So, d square divided by kernel width square. So, here this is a kernel width. Okay. Now, how we what is the value that we have to give it to this sigma? The sigma value here is 0.75 multiplied with under root d. So, from where did we take this? The original LIME paper has used this particular formula. So, it is 0.75 times root d. Now, what is d here? D is a number of features, number of superpixels that you have considered. So, number of features here are 3 for our example. Therefore, 0.75 multiplied with under root 3. So, when you substitute the values, you get this, square of it we get this. Now, how do we calculate the distance, how do we calculate the weight? By using the distance here. So, you go back and then substitute the values. Now, for d 1.732, we are calculating what is the weight. Just substitute the values. We in it is a d square. So, d value is 1.732. Take the square of it, we are going to get this. Then we have also already calculated this. So, substitute the values into this, we are going to get this value. And ultimately, it is w is e to the power of. So, e to the power of minus this whole term. So, minus 1.777. So, we are going to get this value. So, I hope this is clear how to calculate the weights. So, ultimately W is 0.169. So, similar way, now all this is the same value 1.414. For d 1.414, d square is 2, then this fraction we are going to get this much, then e to the power of this value we are getting this. So, since we are rounding off to the next number, we are getting 0.306. Next, for all of this we are calculating d equal to 1, we are getting this wf. So, we are getting this w. Finally, for d equal to 0, e to the power of 0 is 1. So, what we have done, from distance we have calculated the weight. Now, what is that we have to understand from this weight here is, now if you look into none, which means none of the pixels have been considered. If you compare it with the original image is something where all the pixel values are considered, superpixels are considered, and if you consider this, no superpixels are considered, which means the weight will be very small. Now, if you look into these are only small portion of an image is kept, rest of it is masked. So, smaller weights are assigned. If you look into, you have some more information is being added, AB, AC, BC, how close these are to your original image, accordingly it is going to assign the weights. So, the kernel gives higher weights to the samples that are closer to the original instance. If you take this is exactly close to the original, therefore, a larger weight is assigned. Then it gives very lower weight to those samples which are far away. So, if you take this, it is a very small weight, because no superpixels are considered and it is very far away from the original image. Then once we calculate all of this, the next step is whatever the values that we have calculated is then passed to weighted linear regression. We are passing it into weighted linear regression. So, before we go into weighted linear regression, let us quickly do a revision of multilinear regression, so that you will be able to recall the concept to connect to the LIME. So, a quick revision here. What exactly is a multilinear regression? Why the word multi? Because multiple features are considered. And why regression? Because the output is an real number. It is not an categorical, which is not 0 and 1. It is an regression problem. So, here what is the ultimate aim? If the age is 22, 0 experience, the person salary is 3 lakhs per year. If the age is 25, experience is 2 years, then the salary is 4.2 lakhs per year, and so on so forth. Now, somehow we need to understand what is the relationship between this x1 and x2 and how it is connected to y. If we can understand this relation between x1, x2 and y, then tomorrow whatever the new value that we are going to get during a testing, whatever the new value that we are going to get, we can able to predict what is y. Right. In order to do this, first you need to understand, if at all if you get some value 58 and the person experience is 32, then we want to calculate what is the salary. If you want to do this, first you need to understand the relationship between x1, x2 and y. You need to understand this relation. If you can understand this relation, then you can able to easily predict on test samples. One easy way to understand the relationship between x1, x2 and y is a straight line. This is a simplest possible way you can find the relationship between two of these. What is a straight line? Y equal to mx plus c, or y equal to c plus mx. So, this is for a single feature, x is a single feature, but here since there are two features, we are considering x1, x2. Instead of using m coefficient, we are defining that coefficient as beta 1, beta 2. This c term is defined it as beta 0. So, now we have to calculate. If we can find the best values of beta naught, beta 1 and beta 2, then we will be easily we can describe how x1 and how x1, x2 and y are related. The best values of beta naught, beta 1, beta 2 actually describes how x1, x2 and y are related, right. Now, regression has to find the best possible values. How does regression find the best possible values? By minimizing this mean square error. Why we have written a formula like this, 1 by 10, because there are 10 such samples. By minimizing this error, definitely we are going to get the best possible values of beta naught, beta 1 and beta 2. So, now how do regression gets the best possible values? Initially randomly some values will be assigned. When random values are assigned to this, when you calculate y naught, y predict or y hat here, and when you substitute the value, the error will be very large. Then you will update these beta naught, beta 1, beta 2. How do you update these beta values? We use gradient descent. Gradient descent is used whenever we want to find the best parameters. Here which are the best parameters? Beta naught, beta 1, beta 2. And how is that we will compute? We will compute the gradients. What is derivative of error with respect to beta naught? Derivative of the error with respect to beta 1, with respect to beta 2. We calculate the gradients and then we update the beta naught value, old beta minus learning rate and this value. Similar way we get beta 1, beta 2. After we run for some 50, 100 epochs, we are going to get the best beta naught, beta 1 and beta 2 values. Once we get the best coefficients, then let the new value 58 and then 32 come. We will substitute the values. Here it is 58 and some coefficients we have already learnt and multiplied it with 32. Whatever is the value that we get, that is the this particular answer. This is how multilinear regression works. Now, how this is connected? Because whatever we have calculated so far, now go back to the line, coming back to the line, whatever we have calculated the distance, we have calculated the weights. Now, this entire is now passed to weighted linear regression, weighted, the word weighted here, can you see the difference? there is an weight multiplied with that error term. So, it is being passed to an weighted linear regression, and here also the aim here, since the number of features we have considered are 3, there are 3 terms. There are coefficients for each of these features. Now, our aim is to get the best possible beta values. So, how do you get the best possible? By passing it to weighted linear regression. The same concept what you have seen in the previous slide. You are going minimize this error. By minimizing this error, we are going to get the best possible. For example, let us assume the best possible values what we have got is these, right. So, when we write in the equation these this is what is the equation that we have obtained. Now, what we are discussing is not a regression problem, we are discussing a LIME. What is a LIME? It is an explainable AI technique which has to tell which region is important. From this, what are we trying to understand which region is important? The coefficient of A, if you see the value is 0.41, the coefficient of B value is 0.24, coefficient of C is 0.04, which means the LIME explanation is just these beta values. Okay. So, since superpixel A is having the higher value, which means this superpixel A is having a strong positive influence in model prediction. B value is 0.26, which is a moderate positive influence, and 0.04 is a very small positive influence. Why the word we are using a positive? Because all these coefficients are positive values that we have obtained. This is how the LIME works. It will ultimately pass the values to weighted linear regression, and the only difference here is you are multiplying it with the weights that we have calculated. Ultimate aim is to get the best coefficients, and these coefficients will tell us which are the features which are important. Here the superpixels are 3, right? 3 superpixels we have considered. A is having the strong influence, moderate influence, very low influence. So, a quick revision, how did we do? We have first started with segmenting the images into superpixels. We those superpixels which are kept will get the value 1, which are masked will get the value 0. Then we are going to generate and perturbed samples, and these perturbed samples are passed to a black box CNN model, and we are going to get the predictions. Once we are going to get the predictions, we are going to calculate the distance. Once the distance is calculated, we are calculating the weight. Once the weight is calculated, we are seeing that those perturbed instances which are very close will get the higher weights, which is very far away will get the lower weights. Once the weights are calculated, you are going to fit the weighted linear regression, which will give us the best coefficients, and finally you are going to visualize the explanation. Now comes the most important concept we are going to discuss. The full form of LIME here is LIME stands for local interpretable. Why that word local has come? So, if you remember, we had told to remember this important step. Now, the entire calculation, whatever we have done, it all started with calculating the difference, right. Now, how did we calculated the difference? We have calculated the difference by comparing it with the original sample only. What is the original sample? Where all the superpixels are kept. When all superpixels are kept, the value is 111. So, what is this? It is the original instance. With this one value, with this one single instance, the whole line is depending, right. So, from this the first you have calculated the difference. How did we calculated the difference? This played a role. From this difference you calculated the distance. From the distance we calculated the weight. From the weight we calculated the best possible coefficients. So, LIME is local interpretable because the whole calculation depends on this single instance. That is the reason we call it as local. Then SHAP we call it as global. SHAP explainable AI technique we call it as global. Now, why we are calling it as a global? When you look into 0.46, 0.28, 0.06, how did we get these values? We got these values ultimately by considering all of the superpixels. Now, the 0.06, you got it by adding these values. How did we get these values? By considering all of these. How did we considered? We have considered every possible super pixel here. So, if you go back, we the next value. Let us go back to the if you go back to the 0.28, you got the 0.28 by considering all of these. So, LIME depends only on one, but SHAP you are considering every possible superpixel. That is the reason why LIME is called local and SHAP we call it as a global technique. So, and LIME and SHAP can also be applied to an tabulated data, and it can be applied to images, or it can be applied even for text related data sets as well. So, these are the different functions. If you are using on image, we use LIME image explainer, and if you are using on tabulated data, you can use LIME tabular explainer and LIME text explainer if you are working on a text. Similar way, SHAP can be used for tabulated data, then these are the possible functions that we have. If you are working on images, these are the functions, and if we are working on text related, these are the functions that we have. So, with this we have come to an end of this particular session, and in this session we have learnt SHAP and LIME, and in the next session we will be looking into the next explainable AI technique, which is guided backpropagation. Thank you.